everybody. Let's get started. So last time we talked about KD trees, especially we talked about the problems of KD trees in the context of large data sets. So one of the key takeaway messages we talked about last time was when you have a large D, KD trees start to become, quite problematic. The reason was because in case you have only one dimension, then the binary tree, splits the space into, two partitions, each time you branch out of a binary tree. But if you go up to a higher dimension, it gets more complicated. So when D equals to 2, you're, basically splitting the space into 4 partitions. And then when you have a 3-dimensional space, then you have a total of 8 partitions. And as a matter of fact, the amount of partition that we're end up creating is e to the d. So you can easily see that if you have a large dimensional data set, then you're going to have an issue. When I say large, I'm not even talking about like 100,000 or something. I'm when d equals to bigger than 100, you already see the problems of KD trees. When D is large, typically larger than, 5 dimension, 6 dimension, KD tree is probably not the, the best method that you're looking for. And because of that, we introduced this concept of locality-sensitive hashing. The idea was last time to use what is called a hash function, which is the mathematical function over here defined as fx. And what you do is essentially to put the data points into that function fx, and then depending on what the function output is, you could classify the points into different buckets, right? So in this toy example, anything go below the curve, below this line, below this hash function, is going to have the positive sign, and then anything that's above this line will have a negative sign of the hash function. So using that, you can create a hash table where you have 2 buckets basically, and then for each of the buckets we have a list of members. So those are the indices of data points that belongs to each of those beans. So with that, we could see that, locality-sensitive hashing is somewhat better than KD tree. It's quite similar, in fact, but in a sense that in case of KD tree, you're making the partition always along the coordinate basis, right? So you first have to, do the partition along the x-axis, and then you have to do the partition along the y-axis, and then because of that, your way of partitioning the space is not necessarily very effective. Whereas locality-sensitive hashing, the idea is basically to use an arbitrary oblique line to split the space. So instead of relying on x dimension first and then y dimension next, you can just draw a line in a more effective manner. So in a sense that both LSH and KD tree structuralize data distribution into smaller buckets. They are essentially the same, but in a sense that LSH is a better does a better job in splitting the space by allowing an arbitrary sloped lines. LSH can be more efficient, especially when the dimension D is large, and therefore more preferable in big data scenario. We also talk about the issues of exact nearest neighbors and the approximate nearest neighbors, but the caveat of the story last time was that why bother to try to find an exact nearest neighbor, right? We talk about the issue of representing or capturing the human semantic notion of similarity using a mathematical distance function. I mean, there's certainly a limitation in terms of how well you can represent that semantic notion. And if your distance function is not going to be perfect, again, why bother to try to, measure the exact nearest neighbor? So that was kind of the idea. So, we talk about the approximate nearest neighbors and, things like that. What we didn't talk about was the issue of how to find a good line. So, I told you that if this is a data space and you have a data distribution, you could define a line and then using that to, split the data into different buckets. And of course, you can have a family of such lines, which are called a LSH family. And when you have a family of lines, then instead of splitting into 2 buckets, you can have as many buckets as you want. And, and by doing that, you can, make the search much more efficient. But then, how to determine this line, in order to define a line, you need to essentially know the slope and the intercept of the line, and how to find an optimal line that, partitions the space is kind of a question that, you must answer. And the crazy idea regarding this is, okay, I don't know, I'll just throw a random line. Okay. So it sounds really crazy, right? So you have a data distribution, and what I'm going to do is, instead of thinking too hard about, how to define that function, I'm going to just generate a random number to define the slope. And then let's say as a result of that, I have this line over here. And that's basically the strategy that we're going to take to construct the family of LSH. Okay, so, and then, in fact, what you're going to realize soon is that the crazy idea of throwing a random line is not, in fact, really too crazy. Consider this example. So let's say we have 2 data points that are close enough to each other in that data distribution space. So here I'm simplifying it in a 2-dimensional problem, but again, there's no reason for you to assume that this is, this can be generalized to a higher dimensional space. Now, if you think about it, okay, the chance of the 2 closely situated points getting separated by this random line is actually very narrow. Only when the line goes in between the 2 points, the 2 neighbors are going to be separated. Okay, and that's kind of a bad situation, right? We want the data points that are close to each other to be, within the same bucket. And in this case, we end up splitting the 2 close points into separate buckets. So that's not a good, situation. However, if you think about it, the chance of putting these 2 points in different bins is only, this narrow, okay, given that the 2 points are close enough to each other. And then for rest of the cases, they're going to fall under the same bin. So if you think about this, 180-degree angle, in terms of which direction that the line can go through, then only this small slice of pizza over here is the chance where we end up splitting the 2 points into different bins. And then the majority of the cases, we're going to guarantee that the 2 points are, gathered in the same bucket. So in fact, the crazy idea is not, too crazy, since, probabilistically, it's going to be really rare to split the similar points with a random line. So, if you were expecting to see some, fancy optimization algorithm or whatsoever, this might be a little bit of disappointment. But in the world of big data, things are pretty much like this. The fact that you have a large amount of data means, you can be a little less pedantic, and then, you can afford to be, sloppy because you have a large enough data. So the chance of you messing up with, a sloppy algorithm is still very low. So back to LSH. So what happens in an LSH algorithm is essentially we throw a bunch of random lines that pass it through the origin. Okay, so we can have, like I said, multiple lines like this. So in this toy example, we have a total of 3 lines. So these are the family of hash functions. And then using this family of hash functions, now we can divide up the space into, in this example, we have 1, 2, 3, 4 buckets. Okay. Now, when we label those buckets, what we do is to use some binary digits. Similar to the binary one-hot encoding, we encode the bucket labels using binary numbers. So the way it works is actually pretty simple. So let's think about line 1, okay? And then let's think about this bucket over here. Now, this bucket is obviously above line 1, and if I continue to borrow that movie review example, the sign of this bucket is going to be negative, okay? And the negative sign was mapped to 0 in binary annotation. So, with that, the label of this bucket with respect to line 1 is going to be 0. Now, let's consider line 2. And again, this bucket is above line 2. So if the bucket is above line 2, then the hash function value for any point in this bucket is going to be negative, and therefore the label for this bucket with respect to line 2 is 0. So we're going to put another 0 over here. Similarly, if you look at the line 3, still this bucket is above line 3, and then because of the same reason, the label for this bucket with respect to line 3 is 0, 0, 0. And finally, the bin index for that particular bucket is going to be 0, 0, 0. Now, let's take another example, because 0, 0, 0 is kind of boring. So let's consider this bucket now. Again, this bucket is above line 1, so the bin index with respect to line 1 is going to be 0. The same reason the line 2 is below the bucket, and the bucket is above line 2. So the label for this is going to be 0 with respect to line 2. And finally, if you look at line 3 is actually above the bucket, right? And then the bucket is below line 3. And then if you put any of the points in this bucket into the third hash function, the hash function value is going to be positive, right? And for a positive hash function value, we decided to use 1 in the binary representation. So the bin index for this bucket over here with respect to third line is 1. And therefore, the final bin index, the full bin index for this second bucket over here is 0, 0, 1. So if you repeat this process, then, without, too much of calculation, now we know that line 1 and line 3 is above this bucket. So 1 and 3 is above, and then line 2 is below. And then for this bucket, everything is above. So we have 1, 1, 1, okay? And those are going to be the labels for the remaining buckets. So far, so good? So that's how you determine the bin index. Now, the way that the bins are indexed is actually, there's a reason for that, okay? But for now, here's kind of a final hash table that you can create, right, by, using this kind of, bins. So we have, this 0, 0, 0 bucket. We have a 0, 0, 1 bucket. We have 1, 0, 1 bucket. And then we have 1, 1, 1 bucket. And then since we're using the binary digits, we're just, creating an empty table, right? Just to, make it, 8-bit, sorry, 3-bit, hash table. Now, when the query comes in, this is the important part, okay? When the query comes in, what happens now is we, put this query into each of the hash functions. So the query point Q, when we put that in the first hash function, we're gonna see that this is gonna be a positive sign. If you do the same thing with the second hash function, then since the query point is above the line, we know that the value for the second hash function is going to be negative. And then if you put the query point into the third hash function, the hash function line is above the query point, so that's going to be a positive sign. And from that, we know that this is 1, this is 0, this is 1, right? So the bin index for the query function is 101, right? So we know that now the query function falls into this fifth bucket in the hash table. Okay. Now, from this, what we would like to do then is to find the nearest neighbor to the query function. Okay. And then in the lecture slide, it asks the query point is in the bucket 5. Is the nearest neighbor as well in bucket 5? The answer clearly is no. So if you look at the query point is not necessarily within the same bucket with its nearest neighbor, right? So clearly 0.7 is closer to the query point, but the query point is not in the same bucket with the 0.7. So by default, by solving the LSH, by solving the nearest neighbor problem using LSH, you're kind of giving up the accuracy, in trade of, higher speed. And that was a similar situation with the KD tree as well. So in this situation, I mean, one way, like I said earlier, is to just live with it. I mean, when you have a large amount of data, then your chance of, having this inaccurate result is very low. When you have a large amount of data, then, you can easily imagine this space is kind of, packed up with, millions of points. And when you have millions of points, then there's a very little chance that your approximate nearest neighbor is quite different from the exact nearest neighbor, right? I mean, this is kind of straightforward. And like I said, the small amount of error in distance is actually negligible because there's no guarantee that your definition of distance is a precise representation of the semantic notion of similarity, right? So because of that, despite the sacrifice that we're making, it may not actually be a big problem. But for whatever reason, let's say you want to find the most accurate exact neighbors, okay? For whatever reason, let's say you are forced to find the exact nearest neighbors. And in that situation, then the solution is to search neighboring bins in addition to the current bucket that the query point is. Now, the real value of this binary indexing of the buckets comes from this, okay? So how to then visit the nearest bucket to the current bucket? So we have the bit index 101, right? And given this, how do I know which bucket is nearby, which bucket is adjacent to this current bucket? Remember, the reason why you can easily tell this bucket and this bucket is right next to the current bucket is because you have this visualization over here. And that's because you have, only a two-dimensional toy example. Imagine a situation where you don't have such a visualization. The only thing that you have is this table stored in a computer memory. And then, the data space is, I don't know, 100 or, 1,000 dimensional. So there's really no way for you to actually, determine which one is the next, neighboring bucket. You understand my point? Now, the way that we actually indexed the buckets, there's a reason. If you think about it, the neighboring buckets, okay, to the current bucket can be represented using what is called bit flipping, okay? So what I mean by bit flipping is actually pretty simple. So the current bin is 101. What I'm going to do is to flip the first bit. And if I flip the first bit, then it becomes 001. And 001 is this bucket over here in the table. Now, instead of the first bit, let me flip the second bit. Then it becomes 111, which is this bucket over here. Similarly, I'm going to flip the third bit, and as a result of flipping the bit, we have 1, 0, 0, which is this bucket over here. And from a binary bin index to an integer, bin index is an easy conversion, right? So you can easily jump to the neighboring tables, the neighboring buckets, right, by conducting bit flipping. And as a matter of fact, if you look at this bucket over here, 0, 0, 1, 0, 0, 1 is this one over here. 1, 1, 1 is this one over here. So we can clearly see that, they are spatially neighboring to each other. Okay, and then if you look at the bucket 1, 0, 0, the member is empty, so it doesn't really matter that this bucket 1, 0, 0 doesn't exist at all in this space. So in this way, you can actually fairly easily visit nearing buckets to the current bucket by simply just flipping the index in binary. Okay, so that's why we bother to label the bins, label the buckets using those binary digits. Okay, the reason why it ends up becoming a bit flipping is actually pretty simple, because the way that we decided the binary digit was based on if a point is above a query, is above a hash function line or below hash function line, right? So bit flipping geometrically, what it means is, okay, I'm going to flip the first bit. And what that means is I still want to be above line 2. I still want to be, below line 3. But now I want to become above line 1. So which is, my direct neighbor with respect to line 1. Similarly, if I flip the third bit, what that means is I still want to be below line 1. I still want to be, I'm going to flip the second bit. So if I flip the second bit, what it means is I still want to be below line 1. I still want to be below line 3. But now I want to be below line 2 as well. Okay, because previously I was above line 2. And what that means is, I'm going to jump over this line 2 while maintaining the other relationship. So it's kind of a clever way, right, of labeling the bins. And then, by having this way of labeling, you can have a very efficient mean to, jump to the neighboring bins without having to, perform a heuristic to compare, which one is adjacent to each other, and so on and so forth. So that's kind of a get around in case you really want to have an exact nearest neighbor. But most of the cases you don't really need that because most of the cases you just want to have an approximate nearest neighbor, and the chance of you requiring to have an exact nearest neighbor is actually very low. So in a higher level, the LSH algorithm is essentially you begin with a family of hash functions, and then for each member of that family of hash functions, for each of the hash functions, we basically register the training data points as a member of the buckets defined by those hash functions, right? And then when the query comes in, what we do is to jump directly to that bin where the query point is located, and we can do that pretty easily by using a hash function, and the hash functions are randomly initialized. And from that bucket where the query point is in, we do the search exhaustively over there, and then find the one that is closest to the current query point. If you want an approximate neighbor, then you can just terminate the algorithm and then just move on. But if you want to have an exact nearest neighbor, then what you're going to do is then do the bit flipping, and then jump to the neighboring buckets, and do the exhaustive search within the bucket, and then until you consume all the computational budget that you allocated for the nearest neighbor search, you're going to seek for the closest nearest neighbor. And that's basically how the nearest neighbor search algorithm is implemented based on LSH. Okay. Of course, generating just an arbitrary, random functions, I mean, even though that's essentially what's happening, you probably want, to have some better hash functions. So there are actually many variants of locality-sensitive hashing algorithm. So, the most, like the vanilla implementation of LSH relies on the random generation of the slope. And, that's basically how we define the buckets. But there are some other, method where the hash functions are determined in a different manner. So, regarding that, there are some desirable properties as hash functions. In order to be a perfect hash function, you want to have a one-on-one mapping of objects and the bucket IDs, right? And then, you want to have the hash functions to nicely split, distinct objects to different buckets, right? You don't want a situation where, a bunch of different points, a bunch of distinct points are, somehow mapped into the same bucket. Then, you're going to waste your computational time, searching for the neighbors that are in a distant regime, right? So that's, those are the conditions that you want to satisfy. And when you have a family of hash functions, then the probability of collision is defined to be 1 over n. And so n over here is the number of hash functions. And then what that means is, let's say you have buckets defined like this. I should have, you have buckets defined like this. So we have essentially 1, 2, 3, 4, 5, 6 buckets over here. And then if you think about the probability, when you have randomly selected 2 points that are, distinct from each other, then the chance of collision, which means the chance that the 2 points, fall into the same bucket is, 1 over n. Okay. So obviously, if you have a larger number of hash functions, then, the better chance that you can provide a, you can structuralize the data distribution in a better way. But in the meantime, in terms of computational efficiency, it's going to be more complicated because you have more hash functions. So, you have to deal with more neighbors. But in the meantime, if you have too little hash functions, then, each of the bucket will contain so many, data points within the bucket. So then the practical benefit that you can get from having this structuralized representation is going to be marginal. So LSH, we're going to see this soon in an example, but LSH is actually applicable to both type of similarity problems. So if you recall, we talk about 2 different types of similarity search problems. One is the nearest neighbor search problem, which is you have a set of points X, and then, you've got a, query point Q coming from the user, and then based on the distance from Q to all the objects in X, you want to find the nearest neighbor. All pair similarity problem is you don't have a query point necessarily. You just have a set of points in a set X, and then you choose, all possible pairs between those data points in the set X, and then you want to compute the distance, among each other. So in the context of LSH, what you're going to do is then in offline, you're going to create a set of hash functions, and then you're going to hash all objects in X. So that is to create a hash table. So bucket 1 has, these members, bucket 2 has that members, so we're going to create all this hash table in offline. And then when the query comes in, you can rapidly determine which bucket that the query point belongs to. And then we basically find out, which one is the nearest neighbor. In case of the all pair similarity problem, we're going to essentially do the same thing. We're going to create a hash function like this. And then, essentially what happens is for each of the bucket, we're going to find the pairs that are closest to each other. And then essentially we're going to ignore the distance across different buckets. Okay, so that's basically what's going to happen, because usually the all pair similarity problem requires us to find, like top 100 pairs that are most similar to each other or something like that. So you don't really want to bother to, search across different buckets, because then the chance of, finding a pair that is, closer than the current set of pairs is going to be very low. So as such, LSH is a pretty effective way of, structuralizing and indexing a data distribution. And when it comes to the distance comparison, it can be really an effective way of, computing things. So with that, what I would like to do next is, before moving to the next topic, which is the Nystrom approximation, I just wanted to quickly show you how this LSH thing is implemented in Apache Spark. So what I'm going to do is to create a new notebook here. And for this exercise, it's going to be really, quick. So I'll leave it up to you. If you want to, follow line by line and type all this, that's excellent. But if you feel like, I understand that the Zoom meetings are not necessarily, a good way of kind of, following what I type on the screen. So if you just want to watch it, then, that's totally fine by me as well. Now, before that, I will need to prepare a data set. And I'm going to use what is called the movie lens data set. So movie lens data set is a data set that lists lots of movies. And if you look at this, we have movie lens 25M data set. And this data set has 25 million ratings applied to 62,000 movies, and those ratings comes from 162,000 users. So basically, it's a gigantic table that contains, which user rated which movie with what score. Okay. In this example, we're not going to use 25 million data set because that's going to take forever on Colab. So I'm going to use the simpler version, which is the movie lens 100K data set. And if you actually go to the index of unzipped files, u.data over here is essentially what I'm going to need. So if I click this one, then I can see that there are 100,000 rows that contains some numbers. And you may wonder what these numbers are. These are basically numbers. So the first column are the numbers that indicates the user ID. So the user ID 196 rated, the second column is the movie ID. So the user number 196 rated movie 242 with the rating of 3. So 3-star movie. And then I believe the full, score is 5. So 5-star is the maximum, which means this was an awesome movie. And then 1-star is the minimum, which means it was the worst movie ever. And then the scores are basically in between 1 and 5. And then the last column is the timestamp. The timestamp indicating when, which date and time the reviews were left. And then the timestamp is with respect to, this is kind of a, geeky thing. So, the year 1970, January 1st, is kind of a reference time in, many, computing platforms. And then these are basically the number of seconds from that, 1970 date. So, it's basically just the time interval from that reference time. We're not going to use the timestamp, so we don't have to really worry about it. So what I'm going to do is, for those of you who wants to, follow this and, do on your own, I'm going to copy and paste this address to the chat so that you can, do it by yourself. Now, using that URL, what you're going to do is to download, first of all, the u.data file onto your Colab environment. Okay, so it's going to then start to download the data file from that data source. So if you type ls, then you can see that there's a u.data downloaded from the data source. Now, what I'm going to do is actually, I'm going to go to that, code snippet, which I prepared on Icon. So you can simply just copy and paste you know, this thing over here. If you don't want to bother to go icon, I'm gonna just type that in the chat window so that you can just drag and copy. So yeah, so we have this code snippet over here, which allows us to configure Apache Spark on the Colab environment. Now, finally, what I'm going to do is then to read PySpark SQL library, import Spark session, and I'm going to create a new Spark session. So I hope at this point you all know the drill, because you've done already some exercises. So for this app, I'm going to just call it movie app, and I'm going to get or create. So I just created a Spark session, so that's good. Now, what I'm going to do is I'm going to read that u.data, and the u.data is not necessarily a CSV format, but spark.read.csv can, you know, read this u.data without a problem. So I'm going to just use this this thing, and obviously you can see that there's no header included in this. So I'm going to set header equals to false. And then the separator in this case, I think it's a tab symbol, right? So it's not a comma, it's a tab. So the separator for the data is the tab symbol. And perhaps it'll be more convenient to infer schema from automatically from data. So this is going to be what I'll be doing to read that u.data file. And then let's see if I can read the data correctly. It takes a little bit of time because even for this 100,000 smaller subset of data set, it has still 100,000 rows. So it's quite a bit. So it may take some time. But at the end of the day, you will see that there are 4 columns correctly loaded. So if you look at the first row, 196, 242, 3, 196, 242, 3. So you can, maybe I can zoom in a little bit. Let me see if I can blow it up. Yeah, my browser is kind of slow because we have like 100,000 lines of text. So, but you know, you can see that the first row is 196, 242, and 3. The second row is 186, 302, 3, 186, 302, 3. So they're all kind of correctly loaded. One thing I don't like though is the column name. I mean, we can live with it, but you know, it might be better to actually have better naming for the column. So like I said, the first column is the user ID, and then the second column is the movie ID, and then the third column is the rating. So, and then the last one is the time. So what I'm going to do is actually right after reading the CSV file, I'm gonna do a slight modification. I don't know if I introduced this before, maybe not, but df.with column renamed is a function that you can use to rename the columns. So I'm going to rename C0 with user, and then I'm just going to add this renaming function right next to each other. So then C1, I'm going to rename it to maybe movie, and then with column renamed, C2 is going to be rating, and I don't really care about the fourth column, so maybe just leave it like this. Okay. If you don't like to have a super long line, you can break the line and then insert this backward slash, just FYI. Yeah. And then if I do this, then you can see that you know, my table now looks a little better, right? And maybe, you know, let's just select, you know, only the user column, the movie column, and the rating column. Well, I could have dropped the C3 column, but yeah, whatever. Okay, so this is kind of a pre-processing to load up the data. Now, I'm going to move just quickly forward to start generating some well, before that, I think showing the entire 20 rows is kind of, yeah, too much. Now, what I'm going to do is then to create a feature vector, okay, especially for this movie column. So my plan here is I'm going to create a feature vector, and then I'm going to one-hot encode the movie IDs, okay? Because the movie index is basically a categorical variable, right? And you don't want to just use them as is. So it's probably a better idea to convert this movie column into a one-hot encoded vector. So what I'm going to do is I'm going to just apply what we learned last time. If you recall, we used this PySpark.ml.feature import one-hot encoder estimator. So I hope you remember that we talk about the transformers and estimators, right? And one of the things that we introduced last time was this thing called the one-hot encoder estimator. So I'm going to just go ahead and use it without too much of explanation because we've already learned this. So one-hot encoder estimator is going to take the movie column as our input column, and then it's going to produce let's say movie underscore vect as an output column. Now, one option I want to give is by default, when you have n classes, the last class is dropped, and you end up having n-1 dimensional feature vector that encodes that one hot. But this time I'm going to set it false because eventually we're going to compare the Jacquard distance between different users, and if you drop the last dimension, then whichever movie has the last index, it's going to be ignored during that Jacquard coefficient computation. So we're going to set the option drop last equals to false, so that we can create n-dimensional vector where n is the number of movies in our data set. Okay. Now the usage is we all know how to use this. So encoder.fit, because encoder again is an estimator, so you have to fit it first. And then after fitting it, I'm just going to write everything in one line to save some space. So after fitting it, what you want to do is to transform the data frame, and then as a result of that, we're going to have an additional column called the movie vec, which contains the sparse vector representation of that one-hot encoded labels. Okay, so 242nd position has a value of 1, and then the rest of this 1683 dimensional vector is filled with 0, right? So I hope you still remember this sparse vector representation. Now, my strategy here is I'm going to compare the users. I'm going to measure the similarity between the users based off of which movies that they rated positive. Okay, so if, for example, the user 196 has rated movie 7, 12, and 13 to be positive, and let's say there's another user who rated the same set of movies also positive, then we can assume that the two users are similar in terms of their preference. And we're going to use that hypothesis to make suggestions to the users. Okay, so the users are going to be suggested with a movie based off of what other users under the similar condition has watched and rated high. Okay, so that's kind of our action plan. So in order to do that, we need to compare the users, right? And before that, though, the ratings are ranging from 1 to 5, and the action plan is to actually compare only the movies that are rated positive. So what I'm actually going to do is to select by calling df where, and I'm going to select only the ratings that are greater than 3. Okay, or yeah, let's include 3. 3 is kind of okay, right? So the ratings with 3, 4, 5, those are going to be considered as positive ratings, and then we're going to ignore the negative ratings, so 1 and 2. Of course, if we were to make this algorithm more accurate, then we obviously need to consider the negative ratings, but for now, let's just, simplify the problem. So as a result of that, you can see that the ratings are all kind of, positive 3, 4, 5, because we've selected only the ones that has positive ratings. Now, here's a little finicky next step. One thing that you will notice is that the users, of course, provided more than one rating for more than one movie. So what that means is if you actually search through the rows, you will come across user 196, for example, more than one times. Okay. And then 196 may have rated not only just movie 242, but also some other movies. Okay. So we need to somehow aggregate this feature vector and then represent in a way that, let me try to draw something, right next to it. In a way that, let's say, the first movie is, I don't know, Jumanji. The next one is Frozen. The third one is, I don't know, name a movie. I don't remember any of the movies these days. I don't even remember when was the last time I went to movie theater. But anyway, so we have movie A, movie B, movie C, and so on and so forth. And if the user number 1 has rated, say, Frozen and movie A positive, and then rest of the things negative or no response, then this is going to be the feature vector that we'll be creating. Okay. Similarly, if the user 2 has rated Jumanji to be positive, and then no label or negative label to Frozen, nor negative label to movie A, but B and C got positive rating, then this is going to be the feature vector for that second user. Okay. And in order to do that, we need to somehow aggregate, the users, right? So we need to group by the users and then aggregate the sparse vectors, right? So if like for example here, the user 196 has rated the movie 242 to be positive, and then the rest of the things are going to be set to 0 because we're talking about one-hot encoding, right? And let's say, as you scroll down, to the rows, then let's say here's another entry which says user 196 has rated some other movie, let's say movie number 7, okay, as positive, and then everything else negative. So in our data set, we're going to have, such representations here and there, and then we need to somehow aggregate this sparse vector encodings to produce a merged version of the sparse feature vector. Okay. Now, the reason why I explained this, is, well, unfortunately, what you would, try to do from what you learned in the previous class is to maybe just call group by and then, take the summation, right? I mean, that's something you've learned last time. Unfortunately, Spark does not provide summation operation for sparse vectors for some reason. I don't know what that reason is, but I feel like this is kind of an incomplete feature that the developers of Spark has not added, despite the clear need like this. So long story short, there's no way you can take the summation of the sparse vectors. And if you just call, group by user and then sum, it's going to just ignore that sparse feature vector that we just created over here. So that's kind of an unfortunate scenario. But the bright side of that is, well, this is actually a good opportunity for us to talk about what is called the user-defined functions. And the user-defined functions are actually quite useful because, as you can see, Spark does not come with all the features that you may need. So there are certain occasions where you need to define your own aggregation function. And here's the trick. So from PySpark.sql.functions library, you can import what is called a UDF module. And the UDF module is the user-defined function module. Okay, I'm going to show you in a little bit. in the meantime, I need to import another library from pyspark.ml.linear algebra module, and then I'm going to import a sparse vector, okay, because we're going to handle sparse vectors. Now, here is what I'm going to do. First of all, I'm going to, group by. I'm going to group the table by, the user column. And then I'm going to aggregate them by providing my custom function. Okay, so here's where some custom function will go in. Okay, and again, this is going to be a useful trick that that can be very useful later. And based off of that, I'm going to create a new data frame. So let's call it df aggregated. Okay. Now here's my game plan. First of all, I'm gonna collect all the sparse vectors, and then I'm gonna create a list of those sparse vectors. And after that, for those lists, I'm gonna try to aggregate them by defining my custom summation function. So in order for me to collect all the sparse vectors, there is actually another useful library which I introduced a long time ago. It's called spark.sql.functions. And then since this is a long name, I'm going to just give an alias of f. And what I'm going to do here is when I aggregate, I'm going to collect a list of movie vectors. Okay. And then I'm going to produce a new column called movie vector, which means I'm going to just reuse the same column. Okay. And well, let's just do this first. So then as a result of this, what I get to have is I have so what I have over here is an aggregated data table where the sparse vector representations are collected as a list. So for example, here's a user 148, and then you see this square bracket indicating that we have a list. And then in that list, we have a sparse vector over here. And then there are many other sparse vectors in that list. So what I have done is basically I went through the entire rows, and then I collected the rows that correspond to user 148. And then I constructed a list of sparse vectors, which are ready to be aggregated. Okay, we haven't aggregated yet, but they are ready to be aggregated. They are in the format of list. Now, what I'm going to do is obviously then to define my custom function, and I'm going to just call it a vector sum. And then as an input to that, I'm going to receive a list of vectors. Okay. And in that function, what I'm going to do is I'm going to visit all the vectors in a list. So what it means is in this collection of sparse vectors, I'm going to visit all the individual sparse vectors. And what I'm going to do is to, do the summation. And then as a result of that, I'm going to return a summed vector. Now, what I want to explain in this context is that the sparse vector representation relies on this tuple representation, right? So we have the dimension of the vector, and then here's the index indicating the position of non-zero values. And then the third component of the tuple is a list of the actual non-zero values. And we know that our feature vector is a one-hot encoded vector. So there's always going to be just one non-zero element, and then that non-zero element is always going to be 1. So instead of bothering to define a rigorous vector summation formula, what I'm going to do is I'm going to basically just get the indices, okay, indices of the non-zero components, and then I'm gonna collect the values, which are all going to be just a bunch of ones, right? And using that, I'm going to create a new sparse vector. So here's what I'm saying. So for each of the V, I'm going to append the empty list indices by using the V indices. Okay, so V dot indices is going to return this array over here, this list over here. Okay, and then we're going to append this empty list with the V indices in that entire list of feature vectors. And again, I'm going to do the same thing. I'm going to, append the values array, the values list using v.values, which is essentially, these guys. Now, at the end of the day, the indices are kind of messed up because when the Spark collects the entries, it ignores the ordering. So we may end up having the indices kind of all messed up. And then the sparse vector module in PySpark expects the indices to be sorted well. So what I'm going to do is simply to sort the indices. And I don't really need to care about the values because the values are all just bunch of ones. So, sorted or not, it's not going to make any difference. And after that, what I'm going to do is to return a sparse vector that is defined by a tuple, where the first element is the number of the dimension, so the number of elements in the vector. The second is the list of indices. And then the third is the list of values. And that's going to be the way that I will basically merge multiple sparse vectors into one aggregated vector. Now, this function, okay, this function called the vector sum can be transformed into a Spark function that is highly optimized. And that can be done by using this user-defined function library. So UDF of vector sum, okay, is going to create a user-defined, function object. So I'm going to create this user-defined function object as UDF. And then, actually, I forgot to specify the, data type for that function. And in this function, we're obviously using vectors. So vector UDT is a user-defined type of vectors. And that can be loaded from the linear algebra library. So simply just add a vector UDT like this. And finally, I'm going to change the line. Finally, what I'm going to do is to convert that movie_vec column by using that sum UDF object that I just created. So the sum UDF function, the user-defined function, is going to take movie_vec as an input column, and then it will apply this custom function that I just defined, and then it will create a new column called movie_vec, which in turn is going to replace the existing movie_vec column with the aggregated features. So if I run this, then there you go. I see a large sparse vector where non-zero elements are not just one. We have many non-zero elements. And that's basically what you can achieve by doing this conversion. I know it's a lot, but I will upload the source code on Icon so that you can check what's going on. And in fact, if you review it again, you'll realize this is actually pretty straightforward. So I know we have only 2 minutes, so I'm gonna rush up a little bit, but no worries because we're almost there. So with this aggregated, well, I should have not closed that, so I'm gonna just print 3. So with this kind of aggregated, feature vectors, what I'm going to do is going to create a locality-sensitive hashing. So that module is available under pyspark.ml.feature. And then you can import LSH but there are two different versions of LSH. One is called a min hash LSH, and then the other is called a bucket indexed LSH. So min hash LSH is for Jacquard coefficient as a distance metric, and then the bucket indexed LSH is the it uses a Euclidean distance as a distance metric. So in our case, we're going to use simply a Jacquard distance. So here we're importing min hash LSH. And min hash LSH is an estimator. So what that means is, first of all, you're going to create a min hash LSH estimator object where the input column is the movie vector. And then the output column is, let's say, call it hashes. Oops. And then num hash table. So it's a number of hash functions. I'm going to set it to 3. And lsh.fit of df_vec, df_ag, aggregated, right, is going to give us a transformer. And I'm going to transform df aggregated and basically display that result. Oops, what happened? Sorry, I'll put capital C col. Oops, still a problem? Oh, yeah, so many typos. Num hash tables. And as a result of that, you can see that the hash values are evaluated for each of the movie component. Okay. I know it's already 4:45, but I literally have only 2 more lines. So let me just finish that. Apologize for going over time. So, using this, what you can do is, actually, I should have defined the LSH model like this. Okay. And then maybe just show 3 entries. And using this LSH model, what we can do is then to do the similarity search. So LSH model comes with a function called approx nearest neighbors. And then what you're going to do is to basically give the aggregated data frame and then provide a query. And then, specify the number of neighbors that you want to see. Okay. And the query point, I'm going to just define it as a sparse vector, which has 1683 entries. And then let's say movie 1 and 12 that the user rated positive. So what is the closest user in the database to the query user? And then after a while, Spark will return the 3 nearest neighbors to this query point. And that's basically how the LSH is implemented in Spark. So you can see that it has retrieved users that rated the similar movies positively. And then finally, bear with me, just one more line. I'm done here. LSH model.approximated similarity join is going to allow you to compute basically the distance matrix. So I'm gonna, do this over here and then show. And basically it's gonna compare the users in df aggregated with the df aggregated itself. And then it's gonna return the ones that are with the distance value below 0.6. So it's an all pair similarity problem. So the first one was the nearest neighbor search problem. And then the second one is the all pair similarity problem. It takes a bit of time, obviously, because we're basically computing the distance matrix. But after a while, it will return a pair of users that look similar. So we have lots of trivial results where the distance is 0 because we're matching users with itself. But there are columns where the users are identified in terms of the similarity in their preference. So as you can see, the user ID 814 turns out to be similar to the user ID 366. So maybe the movie that the user 814 liked, there's a good chance that the user 366 is going to like this as well. So you can simply actually just filter out the rows with the distance value of 0, and then you can reduce the short list. But for the sake of time, I'm going to stop here